but somehow I cannot pull it out from Blackboard. But I think we had this example. I can't remember the values. I'm going to make them up. Or let's just get rid of the voltage source. Now, let's say this is node A, this is node B, okay? And the question is, what is the equivalent resistance seen between A and B? That's a pure resistive circuit, right? So, now, this is the problem. We have such a circuit, and the question asks for what is the equivalent resistance seen between A to B, okay? Now, if we do our usual approach, we label the nodes, right? This is node A, this is node B, this is completely a different node C, this is completely a different node D. Anything in parallel?
Yes.
Anything in parallel? Not really. Anything in series?
Yeah.
Where?
Yes.
Well, R1, R2.
R1, R4.
Oh yeah, R1. No.
R1?
R1,
Which
R4.
one? R1?
R2.
R1, R2, are they in series?
No.
Why?
They end up in
The
different.
wire.
They don't
I'm
have-
looking at the equivalent resistance seen between A and B, right? Can I lose A?
No.
I can't combine them. Can I lose B? I'm stuck. Okay? When you come to that position, you don't have any parallel resistors, you don't have any series resistors, and you don't know how to reduce this because what you want is, you want that, right? A, B, and you want R, A, B. Okay? That's what you want to find. Now, how to go from this to that? That's what we are trying to solve. Okay? And we talk about series combination, right? You take this A, B, C, you connect this to two resistors with value R1 plus R2 from A to C, or you take parallel combination. This is R1, this is R2, this is in between A to B, and this becomes a resistor from A to B with value R1, R2, well, R1 is parallel with R2, let's say, for the expression. Now, what we have here is, we have now a three-terminal circuit, okay? So this is R1, this is R2, this is R3. What we are claiming is, we can convert it. Well, actually, I think I'm using ABCs for this one. A, B, C. So I have this circuit, okay, and having this A, having this B, having that C, R1, R2, R3. I'm claiming that you can go from this to that or that to this if you satisfy certain equations, okay? If you make sure that, of course, there's a set of equations determining the equivalency, okay? But if you choose, given this circuit, if you calculate R1, R2, R3 in terms of RA, RB, RC, accordingly, this circuit will be equivalent to this circuit based on those external terminals A, B, and C, okay? Now, what are those equations? Well, first of all, is this going to solve our problem? Is this going to solve our problem over there? Let's see. First, make sure that that's going to solve it, right? So, how am I going to do this transformation? Okay, let's say I know how to go from ABCs to 1, 2, 3s over there. How is this going to solve my problem? So, I'm going to take, let's say, this delta. Also, is there only one solution to do that? Not really, right? Here here is this triangle that looks like this one. I can turn this into y, or
The other half.
you can take the one at the bottom, right? You can use the bottom one and then turn this into a y. Does it matter? It doesn't matter. Also, you can claim that here is a y, right? Look at this R1, R4, and R3. Doesn't it look like this one here?
Mm.
The midpoint being this one, right? Or look from here, R2, R5, R3 is also another y, right? You can also convert those y's into the delta versions over there. So which way do you go, or which delta, which y you pick, doesn't matter. This resistance that you're going to end up with is going to be same no matter what you do, okay? So as usual, there are a couple of points. Now, let's see how we place this. Now, let's say I took R1, R2, and R3, okay? And then I convert it into its Y equivalent, okay? This is the new circuit, right? Now, this one, and this one, and this one are gone. I did delta to Y conversion, right? Now, does this solve my problems? Do I have series resistors there? Those two are series, right? Those two series, they are parallel to each other, series to this one. Can I go from this to that? Easy peasy, right? So that will solve my problem. So then the question is, given those three resistor values, what are those values that will make this Y equivalent to that delta? Okay? And you don't really have to memorize this. Unfortunately, I can pull up the PowerPoint. But if you look at the PowerPoint on one slide, you're going to see three equations. One shows how to go from delta to Y. The other one shows how to go from Y to delta. Depending on if you chose a delta and you are trying to transform it into a Y, or if you pick the Y and then you are trying to transform it into a delta. Okay? We have a set of three equations. Why three equations? What?
Three unknowns.
The resistors of what?
Because there's three.
Each branch and then each side of the
Each.
cell.
Almost, right? Fair enough. The three equations, because when you look into that delta, I can define three equivalent resistance depending on
Which delta or what?
which two terminals I look at, right? If I'm looking at the terminals A and B, what is the equivalent resistance C in between A and B?
RC.
With C not connected anywhere.
RC.
Is it RC only?
In parallel with RB and RA.
Exactly, right? If I'm looking at this delta between 2 points A and B, what I see is RC in parallel with RA plus RB, right? Because if this point is not connected anywhere, I don't care about this. I'm looking at the resistance C in between A and B. I can lose C, which means that A and B are now in series. So resistance seen between nodes A and B is equal to what? RC in parallel with RA plus RB, right? Now coming back to here. C is not connected anywhere. I'm looking between A and B. What is the resistance seen between A and B? What is that? The resistance seen between A and B.
R1 plus R2.
R1 plus R2. Why? This is not connected anywhere, right? Any current through R3? Dummy resistor, right? Get rid of that. Then R1 and R2 will be in series, right? So that's going to be equal to R1 and R2. Now, if I'm claiming that those two are equivalent to each other, this expression must be equal to this expression. Okay? You will see a set of equations, a set of three equations for delta to Y or Y to delta transformation. And those equations are obtained through those equivalencies. Okay? Let's do one more. So, if you look into between B and C, what do you see? B to C with A being not connected anywhere.
RA parallel
I have
to
RA in parallel with
RB and
the
RC.
series combination of P and C. So RB plus RC. Coming back here, RBC is equal to the resistor C between those 2 points, with A being not connected anywhere. So this becomes a dummy resistor. So that's R2
and R2.
plus R3. Now, if you make this equation equal to this equation equal to this, and AB, BC, you also need one more for AC, right? AC here. And if you make this one equal to, equate this one to that one, now knowing the values of A, B, C, you have 3 unknowns, right? You are solving for R1, R2, and R3. 3 equations, 3 unknowns, you can solve for R1, R2, and R3. Okay? Make sense? That's how you get the equivalency between those 2 circuits, the delta and the Y. Okay? So you're going to see those equations most of the time, that's all you need. Okay? But if you understand how we are getting that, you're going to be able to kind of like understand what's happening fundamentally here. Okay? So let's do that. The equations doesn't really matter, but what you are doing is over here, you'll take a look at the equations and you will see. But when you are going from delta to Y, so in order to calculate this resistor, you multiply at the denominator. When you are going from delta to Y, the denominator in each case has RA, RB, RC added together. Okay? At the top numerator, to calculate this, you multiply those 2 resistors divided by the total resistors added together. To calculate this resistor, you multiply those 2 divided by RA plus RB plus RC. To calculate this resistor, you multiply those 2 divided by the total resistance. You don't have to memorize that, but that's what it is. Okay, that's what those equations are telling you. Okay? So let's say this is 10 ohms, this is 3 ohms, this is 7 ohms, right? And then the total resistance, RA plus RB plus RC, will be, and you can actually give those names, right? A, B, C. That's going to give you 20 ohms. So if you're actually going to the Y, that's going to be 10 times 3, 30 divided by 20. 1.5 ohm, right? This one over here is 3 times 7, 21, right? 21 divided by 20. And this one over here is 10 times 7, 70 divided by 20. Okay? And then once you get your delta, get rid of the Y. Once you get your Y, get rid of the delta. Now, the equivalency, remember what equivalency is. 2 circuits equivalent to each other means that when you connect something between A and B, okay, let's say you have another device. This device being connected to A to B of this guy, or A to B of this guy, the device shouldn't feel any difference. It shouldn't be able to understand if it is connected to the delta or if it is connected to the Y. That's what equivalency means, right?
Yeah.
So the resistance that the device will see between A and B will be same no matter which circuit it's connected to, okay? And that's why when you are doing delta to Y, you have to be careful. You have to kind of like highlight the part that you are doing the transformation, okay? And by the time you are done with the transformation, all the components, outside components that are left outside of the delta should be connected to the nodes that they were originally connected to. In other words, for those outside components, nothing should have changed. That's why it's important how you label those things. Either do it on the circuit itself so that you're not going to be kind of like confused, right? Or label them, okay? I also have a labeling system there. If you look at those equations in the PowerPoint, it says ABC, R1, R2, R3. Are those random? Anything can be RA? Not really. If you want to go with this labeling system, what I do over here is label A, B, and C, and it doesn't matter. Could be A, C, B, or A, B, C over here. How you put the A, B, C on those three terminals doesn't matter. But once you put the A, B, C's, put RC between A and B, missing letter. Between A and C, B. Between C and B, put A. Okay? Then draw your Y. Again, randomly put A, B, C's. From A to the midpoint, it's gotta be R1. From B to the midpoint, it's R2. From C to the midpoint, it's R3. If you do the labeling that way, you can exactly take those equations in the PowerPoint, okay, and plug in the RA, RB, RC values over here, and then you will get those R1, R2, R3 values and arrange in this way, okay? Because one problem is you can calculate those values, but if you kind of like place them wrong, you're gonna get the problem wrong, right? But I think the easier way is just to do it on the circuit like that. Once you put your delta, then you calculate this multiplied by this divided by the total resistance, this multiplied by the total resistance, and those two multiplied by divided by the total resistance to go from delta to Y. What is the easy way to go from Y to delta? Now, let's get rid of this. Let's say we were going to do Y to delta on that same problem, okay? So that was like this, right? R1, R2, R3. Now let's say I decided to do a Y to delta transformation on this one, okay? So then I'm going to take this part, right? And I'm going to transform this part. Let's say I'm taking this Y over here, R2, R3, R5. R1 and R4 will still stay connected to the nodes that they were originally connected to. Okay, that's not going to change. Now, what is the easier way? Now, on this one, at the numerator, you have R1, R2, and R1, R2s are referring to those R1, R2, R3s over here. R1 times R2 plus R1 times R3 plus R2 times R3. That's for the numerator of each equation, okay? And at the denominator, you have R1, R2, R3. How do you do it on the circuit? You calculate this total resistance, okay? R1 times R2. So in this case, what do we have here? R2 times R3 plus R2 times R5 plus R3 times R5. Let's call this R8. Okay? Or this Y over here. Now, I'm going to divide our total. So what is this going to be converted into? This, right? Because those are my ABCs here. So for the delta, I will have one resistor going from A to C, another resistor going from A to B, another resistor going from B to C. Okay? Now which one is which one? The resistance going from A to C is equal to our total divided by the resistance between midpoint to that other letter that's left out. So I'm going from A to C. I'm going to divide this total resistance by R3. The resistance that I placed between A to B, okay? So this goes from A to B. This is RT. What is left out resistor? R5. Divide by R5. The resistance from B to C is RT. B to C, those R3 and R5 are connected to those. What is left out? R2. Divide by R2. That's how you go from the Y to the delta. And once I do that, then I got rid of the Y. And let's see if this is going to make life easier for me. It will, right? Because now this resistor is in parallel with R1. This one is in parallel with R4. The parallel combinations are in series with each other. So I add those, which is in parallel with RT over R3, right? So I can come down to this. So let's write this down. So now RAB is equal to RT over R5 in parallel with R1 plus RT over R2 in parallel with R4. And this whole thing is in parallel with RT over R3. Any questions? Any questions? Okay, so when you are finding an equivalent resistance between 2 points, if you come to a point, always do not jump into delta to y's if it is not required, okay? Make sure that you really need that. Can you go through a delta to y in a circuit that actually doesn't require, you can. You just get the result in a little bit longer way. So you waste a little bit of time because this is a little bit more time consuming than finding parallel series resistors, okay? But normally, find your parallel resistors, find your series resistors. At the point where you are stuck, you can't find any other parallel resistors or series resistors, then your answer is probably delta to y or y to delta. Okay? Which one to go to go from delta to y or y to delta doesn't matter. Whichever you feel like. Generally, people find it a little bit easier to go from delta to y because it's just a triangle, and then to go from this to that and doing the calculations is a little bit easier, I think. But it doesn't matter. Okay? Any questions? Yes.
How do those equations relate to those equations? Do they?
Those ones?
How do those relate to?
Now, if you label RA, so I did label RA, RB, and RC, and R1, R2, and R3 in a particular way.
Yeah.
If you label them that way, those equations are exactly related to those resistor values. So, in other words, in delta to y, that's going to say R1, R2, R3, right? So your R1 is coming over here, right? Connected to A. Your R2 is connected to B, right? And your R3 is the resistance connected to C. Now R1 will be RB times RC over the total resistance. R2 will be RC times RA divided by the total resistance. And R3 will be RA times RB divided by the total resistance. Okay? Exactly what we did here. This resistance multiplied by this resistance divided by the total resistance. Those two multiplied divided by the total resistance. Okay? And going back, so look at here please for a moment. So when you are going from y to delta, you have this R total, which is R1 times R2, R1 times R3 plus R2 times R3 at the denominator. Now, when you're going from this to this, you have this total resistance divided by R3, okay? So your RC is equal to so this is RC, where you have R1, R2 plus R1, R3 plus, so I ended up writing all equations. RC, and what is going to be the resistance divided by R2? So when you are dividing by R2, R2 is connected to B, right? So the resistance divided by R2 must be the one that's not including this. So it's A and C, so that's RB. And the resistance that you get by dividing the total to R1 is right across this, that's RA. Make sense? Okay? So I mean, you don't have to really memorize this or know this. You can, as long as you label your RA, RB, RCs, and R1, R2, R3s correctly, you can just plug them into those equations, okay, which are going to be in your crib sheet. But if you kind of like see how it is systematically done, it's not really that bad, okay? Xavier, so that answers your question? Okay. Any questions? Okay, then we're going back to our device problems. So we're going to problem, which one? We did the first two, right? Okay, we did 6, so we're looking into 7. Please work on it.
ID.
Yeah, you're right. I was gonna say, don't, whenever we see a problem, don't kind of like, fix yourself on doing standard things, right? Normally, device problem, so what we did last time, we find the model for this device, right? And then replace it in the circuit that it is connected to, and then find the voltages and currents. But you have to first read the question, what the question is asking. The device is modeled with a voltage source in series with a resistance, right? Then the device is connected to a 7-volt voltage source, and the question is, what is the power delivered by the 7-volt voltage source? So let's look at our question first, what we are looking for. Power delivered by the 7-volt voltage source. So I want to label the current through the 7-volt voltage source, correct? Active sign convention. So I'm going to put this as I7. So power delivered by 7-volt voltage source is equal to I7 times 7 volts. All I need is I7. Okay? All I need is I7. Do I know what I7 is? Because see, in the last, the circuit, the question that we looked at, that one previous, before this one, that one was kind of like connected to a more complicated circuitry, right? You wouldn't be able to tell exactly what is the voltage across the device for this other circuit. But over here you can. Do I have to necessarily find the voltage source in series with resistance to solve this problem? Well, someone took this device, right? Already connected this device to different voltage sources, measured that current, and gave me the result, right? So the question is, what is the current now that this device is connected to a 7-volt voltage source? I am given that, don't I?
Mm-hmm.
The only thing you have to be very careful is, you have to be careful with the polarities. So this is a VD versus ID graph with VD and ID labeled this way. According to this polarities labeled there, what is the VD, what was VD refers to over here? That's minus 7 volt, right?
Mm-hmm.
You see that? So VD is defined from A to B. So A is here, B is here, right? So VD for that device is negative 7. Now the question comes down to, for that VD ID graph, what is ID for VD being negative 7? So it is, let me do it with this one. So if you extend this, right? And then this graph goes like that. Somewhere when VD becomes negative 7 volt, what is the ID value? Okay? So if you exactly refer this device to this device, what is labeled from A to B is VD, right? And then how about ID? Is the ID polarity same as this one or no?
No.
Yes, no?
Yes.
When current flowing through device, what is it going through? B to A or A to B?
B to A.
B to A through device. So B here, A here, B to A through device. So ID is same as I7 polarity, right? Okay? Sound good. So this is like my ID, right? And my VD is equal to negative 7 volt. So it all comes down to, for VD equal to negative 7 volt, what is ID? Which is going to be my I7. Okay? How do I get this?
Create slope.
Well, you can solve this equation, right? And then I can get VD in terms of ID and then plug in the VD value for negative 7 and I can calculate ID. So let's do that. That's, you did actually already, right? VD is equal to, what is the slope here?
15 over 7.
15 volts over 7 milliamps, right? 15 over 7 volts over milliamps times ID, right? Plus there's a constant. How do I find this constant? For ID equal to 1 milliamp, VD is 0,
thought it was 8.
right?
It's from 1.
For ID equal 1 milliamp, VD is 0. So if ID is 1 milliamp, VD is 0, what is that constant going to be equal to? Negative 15 over 7 volts, right? Okay? You can check. If ID is 8 milliamps, milliamps will cancel. 8 times 15 over 7 minus 15 over 7, it's going to make 7 times 15 over 7. 7s will cancel. You're going to end up with 15, which is right. Okay? Now that I have this, that's all I need, right? So in order to answer this question now, replace VD with negative 7 volts, 15 over 7 volts over milliamps times ID minus 15 over 7 volts, and solve for ID, that's negative 2.267. Milliamps. And that's all I needed. You plug this in, and the power expression, power becomes negative 15.87 milliwatts. Use it here. Okay? Any questions? So be careful if you really, well, another solution would be what? Another solution would be what? What else could you do? What else could I do? Is that all I got? I know more than that. How did we do it last time?
Create the model.
Create the model, right? So I could also do, well, I didn't use this information at all, right? I really didn't need what's inside the device, because if the question asks me what is the device model first, then I have to actually use this and find that. But all it asks for me is power delivered by the 7 volt. All I need is the current through that 7 volt. So I didn't need anything else actually other than that. But what I could do also, it's a voltage source in series with a resistor, right? So delta VD, let's call this VSRS. So let's say this is A, this is B. This is A to B, VD. Through device, B to A, this is ID. Right? So this gives me two equations. Well, actually one equation, one KVL equation, right? ID times RS plus VD minus VS is equal to 0, correct? Then I know two ID-VD pairs over there. For ID being 1 milliamp, VD becomes what? 0 minus VS equals 0. For ID equal 8 milliamps, what is that? 15 volts minus VS equals 0. Equation 1, equation 2, solve to get RS and Vs. Once you get the model, now go to the circuit that it's connected to, replace your device with the model, right? How do I do that correctly? Be careful, the device is flipped, right? So what I'm gonna be doing is, my original model, how I picked, the B side has the minus sign. Don't forget. So the B side should have the minus sign here, right? Resistor is in series, right? It doesn't matter if I put it here or here. So that's RS, that's BS. Okay? If I do it that way, I don't really have to think what is VD, what is ID. I don't have anything to do with VD and ID now. I already used the VD ID values over there to get those values, to get the model. Okay? So now I have the circuit, I have the voltage source value, I know the resistor value. All I'm looking for is this current. You write your KVL equation over here, right? And then you get your value. That's another way of looking at it. Okay? That's a little bit longer since you have to go through that, but it's okay. Both are solutions. Okay? Any questions? Okay, keep going then. The other question.
Actually, why do we use -7? Isn't it when we find the power, we just use
Why are we using
-7 instead of just 7?
this one over here? Because if you are going with this other way, right, what VD refers to in the given model is the voltage from A to B. If you're going to use this graph to get this current, right, you have to exactly use the same polarity for VD that this graph uses. And this graph uses this polarity where VD is labeled from A to B. This not being A, this not being B, VD becomes this voltage, right? And this voltage is not +7, that's -7 volts. Okay?
I have a question.
Yes.
Well, for question 7,
This one that we did? Uh-huh.
if I want to calculate the power absorbed by the device, is that equal to -ID times VD?
Well, we didn't actually quite finish the problem, but we didn't need much over here. Now, in that circuit, how many components do we have? If you count this device as one, because we're talking about the power absorbed by the device, right? There is device and then the 7-volt voltage source, right? Now, if this one is delivering power, what should this one do? Absorb it, right? So the power delivered by this one, doesn't matter if it is positive or negative, it's going to be equal to what? Power absorbed by the device, right? Also in those questions, when it asks, I think, yeah, that's what we have also in that new problem that we're going to discuss now. When it asks for the power absorbed or delivered by the device, remember that device is composed of two components. One big mistake that's generally done is, when the question asks what is the power absorbed by device, people generally would calculate the power absorbed by this voltage source, and that's wrong. That's actually missing. Okay? Device is composed of this resistor and the voltage source. Okay? If you go back to the beginning of this class, when we gave you a device like that, right? Let's say device D, and if I ask what is the power absorbed by this device D, what would you do? You would have your voltage, VD, your current, and passive sign convention, it's VD times ID, right? Doesn't matter what's inside here. Same here. So if you're calculating power absorbed by this guy, it's gonna be VD, well actually minus I7 times VD. VD being the voltage across both components, not one of them. Make sense? Okay? That was your question or no?
Yeah, that's
Okay. So let's look at that, and then we're gonna look at that again here. So this is A plus minus AX. scenarios, right? All I need is two scenarios to find a model for a device. Two unknowns, two scenarios where I get two equations. That's all I need. So I have two different circuits over here. The first circuit, the information that I get from the first circuit. Read the question. So first of all, that's voltage source in series with a resistance, right? A resistor and a current source are connected to the device. So it's the same thing that I was doing. Normally in those graphs where you have VD, ID graphs, right? What you generally have is you have this voltage source, something connected, and then you're reading the ID, right? In that case, I didn't do that, but what I did was I connected a resistor in parallel with this current source, and I measured the voltage. That's my first measurement, first experiment. Okay? So we're gonna write an equation from this data. Then I took the same device, I connected a 3 milliamp current source, and I measured the voltage across nodes A and B, and then it happens to be 4 volts. You are given this one too, and that's the second experiment. That's all I need. Okay? Two measurement results given to me. I'm going to use this data to write two equations to solve for two unknowns. What are the unknowns? What are the unknowns that I'm trying to solve for?
The voltage source and the resistor.
Voltage source and the resistor that's in series, right? So let's define those voltage source and then resistance. So let's call this VS, RS. Again, the polarity over here doesn't matter. I have to stick with it though. So this is AA. Be careful, sometimes the devices are flipped. RS plus minus VS. Okay? And maybe let's do this that way. That's easier. Confusing. Get rid of the device here. I replaced my device with its model. So now I'm trying to figure out the model. Okay? So we are trying to find a device model in part A. Now the equations. What do I get out of this? What can I write here?
Write a KCL and a KVL.
I can write a KCL equation here, right? Okay, so then let me define a current. So let's define this current. Do I have anything? IS? No. KCL gives me what? IS plus 5 milliamps plus what else?
IL.
IL, which could be, I can already write that in terms of something else, right? Like things that I know.
8 over R.
So voltage equal to current times resistance, right? For the resistors, if I know the voltage, I know the current. I know the current. If I have the current, I know the voltage. So this is equal to, just be careful with the polarity, 8 volts over 2.2K flowing down. 2.2 kilo ohm equal 0, right? I didn't use VS in my equation yet, right? So then I can calculate actually IS from here, right? Right? And then if I know IS, now I can do my KVL, negative VS, negative IS times RS, plus 8 volts is equal 0. And with the IS value known, that's my equation 1, with the unknowns being VS and RS. Okay? Yes.
So why is not like negative 8 volts minus 2.2?
Why this is not negative?
Yeah.
Because 8 volts over 2.2 kilo ohm will be that current flowing down, right, in passive sign convention. And I'm writing the KCL at that point, right? Leaving the node, that's why plus. Okay? This is equation 1. Now equation 2 comes from this circuit over here. What can I write here? What equation can I write from the second circuit? A KVL I'm gonna write, right? So this one is negative VS. Do I know the current through RS?
Yes.
That's the current source, right? Through current source that's flowing that way. So what do I have? Negative RS times 3 milliamps. And the voltage across the current source given plus 4 volts. So that's my second equation. Again, the only unknowns are Vs, Rs. Solve 1 and 2 for Vs and Rs. And 5.031. That's what my Vs. And then look at the circuit question. It says draw the circuit showing terminals A and, well, it doesn't say, but find a device model showing terminals A and B. So your final answer when it asks for the device model should be this. Vs equal to 5.031. Rs, negative resistance, negative 343.76 ohms. And this was my A, this was my B. That's the answer for part A. Okay? Now in the second part, we are connecting the circuit to that, the device actually to that, and we are looking for power delivered by the device. Okay? Do I want to work with this? Not really, right? Let's just reduce this, right? So what can I do? Tell me.
Get rid of R11 and 12.
Get rid of R11 and 12 first of all. Don't have anything to do with those nodes, even though Vy is defined. I don't have anything to do with Vy, right? So open circuit, open circuit. What else?
R1 and 3 are
Now,
in
if
series.
this is gone, R1 and R3 are in series, right? And I don't really care about this node, do I? And the series combination will be shorted out, right? So these are going to be short circuit. What else? Now I can actually redraw. Where should I redraw? Now that we have the model, let me erase this part. So here is our device. Node A, node B. Before I redraw, what should I do?
I'll label all the nodes.
Should label the nodes, right? So if this is A, this is B, so all this is B. Now this one is a new node, C, right? This one is D here, and this one is also D. That's it, right? Now let's redraw. So A to B, what do I have? We're doing a resistor reducing practice, R4. A to B, R2. B to D, B to D. 8 and 9. What else? B to C, B to C. What was it? B to C, B to C, parallel. What is that? C to D. So D is here. Didn't do a good job, did we? Okay. So C to D, R10, R7. Okay? Good? So let's get rid of this part. We're gonna redraw one more, right? Okay, so because I want to keep A to B, right? So what I'm trying to do is I can get rid of any nodes other than A and B, right? A and B, I don't want that. A and B is where I'm looking at the device. So we're actually looking for the resistance, equivalent resistance seen by that device. Okay? That's another way of saying that. So I'm gonna put my R4. I'm not gonna touch that yet. Okay. So what else do I have? Let's combine a couple of steps together, okay? Let's put R2 also. So R4 and R2 are gone. Let's combine those into a single resistance. What do I have?
R5, R6 are in series with R2, R7.
So I have those two resistors in series, right? The middle node is C. I can get rid of that. Once I combine those, that's going to be a resistance from where? B to D, which is going to be then in parallel with that, right? So B to D, I have this resistor. Let's combine them all. And I have R8 in parallel with R9 in parallel with the series combination of R5 in parallel with R6. The parentheses are extremely important during that procedure. R10, and then in parallel with R7. Okay, that's it. Almost done. So if we do one more step, we can find RAB being equal to, so let's give this a name. This says RBD. So what do I have for the final resistance? RBD plus R2 in parallel with R4, right? So R4 in parallel with R2 plus RBD. 7.17. That's what resistance is. So that's the resistance connected in between A and B, right? So I'm gonna take this, connect this to here. Okay. Now, given this circuit, what is the power delivered by the device? Tell me what I should label. Current, okay. Which way? Going up or down?
No. It's better.
I don't have the voltage yet, do I? I'm not trying to find the power delivered by that, right? So it doesn't matter really because I didn't label the voltage yet. So let's say I put this over here that way. Okay, IS. Well, there are a couple of things you can do over here. Okay? One, which is I think the easy. Well, let's go through the longest one first. Okay? Power delivered by the device. Device consists of what? VS, right? So finding IS, you can find the power delivered by VS, then you can find the power delivered by RS, you can add them, that's going to be the power delivered by the device. That's one way to go through it, right? So let's just write the expressions. Power delivered by VS will be equal to what? ASVS, right? Tell me what is the power delivered by RS? Huh?
Minus ISR.
IS squared, right? Minus RS IS squared, right? Power delivered by the resistor. And if you add them up, that's going to be power delivered by device. What's an easier way?
Find a voltage across the entire device.
You can find the voltage across the entire device, right? Which is this. Let me pull this VAB.
The device.
What is the power delivered by the device in this case?
VAB
IS
bias.
squared.
V. What? What is?
Negative
IS
3
squared times 7.1.
So in that case, open this, right? This is your device. So if this is your device, this is node A, this is node B, so this is your VAB, and your IS is defined this way. What is the power delivered by the device? IS times VAB, right? Everybody's okay with that? Another way, the third way, huh? No way. How many components do you have here? 2 components. Power has to be conserved, right? If you're trying to find delivered power by that, what is that equal to? Absorbed power by the resistor, right? So once you get IS, what is the absorbed power by this resistor? IS squared times 7.17, right? That's power absorbed by that, which has to be equal to power delivered, which is the power delivered by the device. I think that's the easiest way to go. But that just because that happens, just because you have 2 components here, just a device and another component. Otherwise, you wouldn't be able to do that. Let's say you have tons of other components, you are looking for the power associated with the device. Your best approach is to label the voltage across the device, current through the device, and then find what it's equal to. Okay? Question? Great question. Yes.
The power delivered by RS, why are you making it negative?
What is the power delivered by power absorbed by RS?
RS times IS squared.
Yeah. So power absorbed by a resistor. Remember that we discussed the power absorbed by a resistor, and we said that's going to be either VR squared over R or IR squared times R. But because those are squared, for a real resistor, it's always positive, right? So that's why I made it negative. Okay? Any other questions? So let me just write this down here. That's one way, or power delivered by device is going to be equal to power absorbed by RAB, which is equal to IS squared times 7.17 ohm. And the value is equal to 1.6 milliwatts. Okay? And we didn't discuss how you get IS, but do do your KVL equation over here and you get IS value, right? Okay? There's one more left. So we're gonna look into that last problem, okay? And then I'm gonna talk about the VDR and CDR, and then we're gonna finalize this topic on Wednesday.